Hey y'all, in this lesson, we're going to be orienting ourselves with the coordinate plane. The coordinate plane is a flat surface with X and Y axes on it. And with those two axes, we can plot points. We can do lots of stuff on a coordinate plane. One of the things we can do is plot points. And a point is written with X, comma, Y. And we call this a point or a coordinate. A coordinate plane has an x-axis and a y-axis. The axes meet at the center, which is the origin. And the coordinate of this point is 0, 0. It's the dead center. So I have a little picture here. I wish he was smiling. I could make him smile, but that's okay. I have a little picture here, and we're going to practice writing coordinates of specific points based on this cute little picture. If you're smiling, it's a little smile. That looks way worse. So he's a little teddy bear, maybe. Anyway, so point A we locate is right here. And when we write a point, it is X, comma, Y. So this point is representative of the X value 2 because, rewind. This is the X axis. You can see the little X right there. This is the Y axis. You can see the little Y right there. And basically what we have to do is X, comma, Y. So we walk into the building and then we go up or downstairs, depending on where the point is. In this particular case, we go over 2 on the x-axis, up to 5 on the y-axis. So we walked into the building, 2 feet, and then we go upstairs 5 floors, x, comma, y. And you'll do this for every single point. Now, these values, just to give you some more information, these are the positive X values. And then these are negative X values. This is the center, the origin. And down here, we have negative Y values. And up here, we have positive Y values. So wherever your point is in the coordinate plane, whichever quadrant it's in, depends on the sign of the numbers for your X and Y coordinates. So just be careful with that as you fill out the table to the right. So go ahead and pause the video, try to fill out this table, come back and check your answers. Okay, check your coordinates. Make sure that the signs of the X and the Y coordinates match what I wrote on mine. Just a quick example here. Point D is right here. We walk over 3. We go down 1, and that's why it's a -1. So just check your answers real quick. If you need to pause it and check it, that's fine. So I mentioned earlier the term quadrants. The coordinate plane is split into 4 quadrants. Quad means 4, so that makes sense. And these quadrants are written in Roman numerals, which you may not be familiar with, but it's not too hard. So if we're going to label these quadrants, and the reason why this is important is because sometimes we refer to quadrant 1 or quadrant 2 or whatever. It's good to know where that is. We start in the positive quadrant, and that's quadrant 1. And then we work counterclockwise 2, 3, 4, and 4 is the only one that you might think, what? Why is that 4? But it's just a Roman numeral for 4. This is a 5. The 1 before it subtracts it, makes 4. You don't have to know Roman numerals. You just have to know how to recognize it on a coordinate plane. And so we could say that point E is in quadrant 4, or point G is in quadrant 3. And that's kind of the extent of that for this lesson. Now, for any given function, a table of values can be built as a list for a set of points, kind of like the one we saw above. This is a different kind of table, but we have this list of points that kind of gives us a map as to what our function looks like or our graph looks like, depending. A table of values is usually a T chart with x's, or the independent variable, on one side, and y values, the dependent variable, on the other side. Now, it may not always be x and y, so that's why I clarified and said independent and dependent, because it may be a and b, or y and z, or s and t. It just kind of depends on the problem that you're looking at. There we go. You can choose, if you're building a table of values, you can choose whatever x values that either make sense to the problem or are in the domain, or that if you don't have to look at that specifically, then you can just choose whichever x values that you want to choose. And I did mention, x values within the range of the problem or the domain of the problem. As we go further into tables of values, you want to be a little bit strategic about the x values that you choose, so that you can get a better idea as to what your function looks like. For today, though, it doesn't really matter. We're looking at linear functions, and those are pretty, there's no values restricted in the domain, so we can use all the x values. You don't have to worry about all that. But for long story short, for the sake of this lesson, you can pick whichever x values you want, or independent variable. But whatever x value you do choose, this does decide the y value, which is why the y value is called dependent, because the y value is dependent upon whatever x value you choose to use. So if we build a table of values for this linear function with y equals 2x minus 9, I can pick any x value that I want. There's no x values that are going to be restricted from the domain, so I can pick anything. It's all fair game. I can pick negative values, 0, positive values. Just to get a good representation of everything, I'll do -1, 0, 1, and 2. I generally will pick values that are close together. And I'll also generally pick values that are pretty easy to plug in. Small numbers. Small numbers are nice. And y is going to depend on these values. So all I know about y at this point is that y equals 2x minus 9. Now I said x, but I wrote -1, because in this particular instance, I'm saying that I'm using -1 as my x coordinate of this point that I'm trying to find. And then I'm going to simplify that. -2 minus 9 is -11. So the y coordinate of this point is -11 based on the -1 that I chose. And then we just do that for all the other x coordinates. So go ahead and pause the video, try the rest, come back. Remember, when you substitute those x values in, that we do have to take into consideration the order of operations. So you have to do that multiplication part first, then subtract 9. So we have 0 minus 9, 2 minus 9, and 4 minus 9. And this gives us, this would be the table of values that you would see. This box, or this column over here, this would be kind of your side work that you're not going to see. If we were to pull up the calculator table of values, you would just see x and y, and there would be a lot more points. It goes on infinitely in both directions, so there would be a lot more points. These are just 4 of the points that I chose that live on the line. And so I could use those 4 points. I didn't put it on here, but I could use those 4 points to plot on a coordinate plane. I'll just do a little sketch here. And I could connect those 4 points to get a visual representation of this table of values. And like I said, there are infinite number of points on this particular function. These are just the points that I chose. So -1 would go down to -11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, way down there. 0 goes down to -9. 1 goes down to -7, and 2 goes down to -5. And you can see here that these points have a linear trend. And on that line are, you might have chosen, any of the other points on the line, but our picture is just exactly the same because we're all going to get the same points. All right, so let's use that idea to answer these next two questions. Is 2, -7 on the graph of y equals 2x minus 11? Now, there's several ways you can approach this, but the easiest way is to use substitution. If this represents x and this represents y, and then they gave me an equation with x and y in it, then all you have to do is substitute it in. And if it comes out to be a true statement, then yes, that point is on the line. If it comes out to be a false statement, then no, it's not. The other way you could do this is just build a table of values that includes 2. And if the y value is -7, then yes, it is on the line. So we have y equals 2 times x minus 11. So I took the y value and plugged it in for y. I took that value and I plugged it in for x. And now I have -7 equals 4 minus 11, which is true. So yes, 2, -7 is on the line y equals 2x minus 11. And again, if you were to just build a table of values for this line, then find this point in your table of values. So use that example to help you solve the next one. Pause it, try it, come back and check. What you should have for your first step is you're just substituting in x and y for x and y. So when we substitute, remember that we kick out the variable and we plug in the value that we're trying to substitute in. So we plug in 3 in place of x, 5 in place of y, and we're trying to see if this does equal 14. I should have put a little question mark up here. It's fine though. And so we multiply first. 9, 3 times 3, 2 times 5. Does this equal 14? No. No, it does not. So 3, 5 is not. That T got funny. Looks like a Greek letter. Not on the line 3x minus 2y equals 14. So again, if we were to do a table of values for this linear equation, we would not find 3, 5 in that table of values. Or if we were to draw the line on a graph, we would not see that point on the line. That's all I have for this lesson. I hope you enjoyed it. If you have any questions, please let me know and I'd be happy to help. See you in the next one.